Right now, above whatever roof is over your head, the sky is doing something it has been doing since before Earth existed, quietly leaking the oldest light in the universe into the space around you. You can't see it with your eyes, but it's there, arriving from every direction at once, a faint afterglow from a moment so early that stars themselves hadn't been invented yet. Tonight, we're going to travel through the strange, patient, astonishingly measurable science of astrophysics, the discipline that takes the universe's grandest, most impossible-sounding ideas, bending time, invisible matter, light older than any star, and turns them into something you can actually calculate, test, and trust. Hello, and welcome to Somniora Mind. I'm glad you're here. Before we drift outward into the cosmos tonight, if these long, gentle science journeys help you unwind, consider subscribing or leaving a comment or tapping the like button before you settle in. It costs nothing, and it helps this quiet little corner of the internet find the people who need it most. Now, let your shoulders soften into whatever is holding you up. Let your breathing slow down on its own, without needing to be told to. And let's begin. Here's what we'll uncover tonight. We'll find out why looking at the night sky is secretly a kind of time travel, and why some of the light reaching your eyes tonight began its journey before Earth had finished forming. We'll discover why every atom inside your own body, the calcium in your bones, the iron in your blood, the oxygen filling your lungs right now, was forged inside a star that died long before our sun ever existed. And near the end of the night, we'll sit with one of the strangest ideas in modern physics, that a black hole, the darkest object the universe can produce, might not be a permanent prison after all, but something slowly, patiently leaking itself back into existence. Here's a number to open with. If the sun somehow vanished this instant, Earth wouldn't notice for about 8 minutes. Not because nothing would happen, but because even gravity itself has a speed limit, the same speed limit light obeys, and the universe simply refuses to let cause and effect travel any faster than that, no matter how urgent the cause might be. Let's start with light itself, because nearly everything else tonight depends on understanding what it's actually carrying. Every time you look at the night sky, you're not looking at things as they are right now. You're looking at messages from the past. A nearby star might show you light that left its surface only a few years ago. A distant galaxy might show you light that began its journey before Earth had even finished forming, arriving now, tonight, having crossed billions of years of empty space just to land on your retina or on the mirror of a waiting telescope. Light moves extraordinarily fast, but the universe is so vast that even light needs real, measurable time to cross it. This turns an ordinary telescope into something closer to a time machine, one that doesn't move through time itself, but instead collects old light, letting us read what some distant corner of the universe was doing long before anyone here was watching. The oldest light of all doesn't come from any single star or galaxy. It comes from the universe itself, from a time before stars existed at all. In its earliest moments, the cosmos was so hot and so dense that it was filled edge to edge with charged particles, constantly scattering light in every direction, more like a glowing fog than an open, transparent sky. As space expanded and cooled, electrons finally settled into orbit around atomic nuclei, forming neutral atoms for the first time, and in that instant, light was finally free to travel without being endlessly scattered. That first, freely traveling light has been moving through space ever since, stretched by the universe's ongoing expansion into faint microwaves, far weaker and colder than visible light, but still detectable today, arriving from every single direction in the sky at once, not from one distant point, but from everywhere, because it comes from the early universe itself, surrounding us on all sides. Astronomers call this the cosmic microwave background, and its tiny, subtle temperature variations mark where matter was ever so slightly denser in that ancient fog, variations that would later grow, over billions of years, into every galaxy, every star, and eventually, into you. In a very real sense, the night sky is still quietly displaying a baby picture of the entire universe, taken long before anything recognizable existed to smile for the camera. Space itself, meanwhile, isn't just an empty stage that galaxies happen to be flying across. The distance between faraway galaxies keeps growing because space itself is expanding, stretching the fabric those galaxies sit within. This single idea completely rewrote humanity's picture of the cosmos. Instead of a fixed, static backdrop, astrophysics revealed a universe built on a genuinely dynamic, ever-changing fabric. As light from a distant galaxy travels toward us, that ongoing expansion stretches its wavelength, shifting it toward the red end of the spectrum, an effect called redshift, and the farther away a galaxy is, the more dramatically that stretching shows up in its light. Given enough time, some galaxies will recede so far, so quickly, that their light will simply never manage to catch up to us at all. They'll pass beyond what astronomers call a cosmic horizon, not because they've crossed some physical edge out there, but because the space between us and them is expanding quickly enough to outrun their own light entirely. Some far-future civilization, living in a much older galaxy, might eventually look up and see a genuinely emptier sky than the one we get to enjoy tonight, its neighboring galaxies having quietly slipped beyond the reach of any signal they could ever receive. All of this comes from careful, repeated measurements of real light, not speculation. The universe isn't merely large. It is, right now, while you rest here listening, becoming steadily larger still. There's another idea worth sitting with here, one that quietly reshapes how you might think about gravity itself. It's tempting to imagine gravity as something instantaneous, an invisible connection linking every mass in the universe all at once, updating everywhere the moment anything moves. Modern physics says otherwise. Changes in gravity travel through space-time at exactly the same speed as light, no faster. If the sun somehow vanished this very instant, Earth wouldn't simply stop orbiting it right away. For about 8 minutes, our planet would continue along its usual path as though nothing at all had happened, simply because that's how long it takes for both light and gravitational information to cross the 93 million miles separating us. This doesn't mean gravity is weak or uncertain or somehow less real than we thought. It means the universe enforces a genuine speed limit on cause and effect, one that applies just as strictly to gravity as it does to light itself. The same principle is what allows gravitational waves to ripple outward from merging black holes and colliding neutron stars, not instantly, but as real, physical disturbances spreading outward at the same cosmic speed limit that governs everything else. It makes gravity feel a little less like an invisible rope yanking objects together, and a little more like a genuinely dynamic property of space-time itself, one with its own travel time, its own patience, its own built-in delay. That same warping of space and time becomes even stranger near a black hole, where gravity doesn't just pull, it changes the very pace at which moments pass. This comes directly from Einstein's theory of relativity, where space and time aren't separate, fixed backdrops, but a single, flexible fabric that mass can genuinely warp and stretch. Far from a black hole, an ordinary clock ticks along exactly as you'd expect. Move that same clock closer, though, and to someone watching safely from a distance, it would appear to run measurably slower, its ticks stretching out, its rhythm gradually slowing as it approaches the boundary where escape finally becomes impossible. To the person actually falling inward, time might feel completely ordinary the entire way. But to the universe watching from outside, their entire descent would seem to stretch and gradually fade from view, without ever quite appearing to actually finish crossing that final boundary. This isn't some illusion caused by faulty clocks or delayed signals. It's the universe genuinely keeping time differently in different places, depending on how deeply embedded in gravities while those clocks happen to sit. It sounds almost like fantasy, and yet this exact effect is built directly into the mathematics engineers use every single day to keep GPS satellites correctly synchronized. A small, practical reminder that even here on Earth, time is never quite as fixed a background as it feels. Let's come back down to something a little more familiar now: the stars themselves, and the strange, delicate balancing act that keeps every single one of them from either exploding outward or collapsing inward at any given moment. A star survives because two enormous forces have reached a kind of ongoing, delicate agreement. Gravity pulls everything inward, constantly trying to compress the star under its own tremendous weight. Deep inside its core, though, pressure and temperature climb so high that atomic nuclei fuse together, releasing energy that pushes back outward, generating exactly enough pressure to resist that inward collapse. For most of a star's life, this balance holds steady. The star doesn't explode, and it doesn't cave in on itself, because these two forces are locked in careful, ongoing negotiation. Our own sun sits comfortably in this long, stable middle phase right now, steadily fusing hydrogen into helium, the same quiet process it has maintained for roughly 4.5 billion years already. If fusion happens to slow, even slightly, gravity gains a little ground, and the core contracts. If fusion happens to surge, the star expands outward until the balance settles again. This equilibrium isn't fragile in any ordinary sense. It can hold for billions of years without serious disruption, but it cannot hold forever, and when a star's fuel finally runs low, that long-standing agreement breaks, opening the next, often far more dramatic, chapter of its life. Every second, deep in the sun's core, hydrogen nuclei fuse together into helium, and the resulting helium nucleus ends up weighing very slightly less than the ingredients that built it. That missing mass hasn't simply disappeared. It has become energy, following Einstein's famous relationship between mass and energy directly, and the sun releases that energy outward as radiation, including the very light that warms your skin and, indirectly, powers nearly all of life on Earth. Millions of tons of solar mass get converted into pure energy every single second inside that core. It sounds like an unsustainable rate, and yet the sun is so genuinely massive that it can continue this exact process for billions of years still to come. That light doesn't escape immediately, either. It begins deep in the core as extraordinarily high-energy radiation, then spends an extraordinarily long time working its way outward, bouncing and scattering through countless interactions, before it finally escapes into space and eventually reaches Earth. When ordinary daylight touches your skin, it's carrying, quite literally, the result of nuclear fusion that happened inside a star 93 million miles away. The sun isn't burning the way a log burns in a fireplace. It's slowly, patiently turning a tiny fraction of its own mass directly into morning. That same sun doesn't only send us light. It constantly exhales a steady stream of charged particles outward in every direction, called the solar wind, expanding outward through the entire solar system and carving out an enormous, invisible bubble in the surrounding interstellar gas, called the heliosphere. Earth's own magnetic field mostly deflects this steady stream harmlessly around our planet, though some particles do funnel down toward the poles, colliding with the upper atmosphere and producing the shifting, glowing curtains of the aurora. Far beyond the outer planets, that solar wind gradually weakens until it can no longer push back against the faint, ancient gas drifting between the stars. Two spacecraft launched in the 1970s, Voyager 1 and Voyager 2, have both, remarkably, already crossed that boundary, becoming the first human-made objects to leave the heliosphere entirely and enter true interstellar space. They're still traveling outward tonight, carrying a golden record of Earth sounds and images, moving at tens of thousands of kilometers per hour, and yet, at that pace, they would still need tens of thousands of years just to reach the distance of the very nearest other star. It's a strange, quiet thought to sit with. Two small, aging spacecraft, launched before most people alive today were born, are still out there right now, drifting silently through the space between stars, carrying a small, deliberate message from Earth, addressed to no one in particular, and to whoever might, someday, happen to find it. Not every star burns at the same steady, patient pace, and the differences turn out to be almost the opposite of what intuition suggests. A star carrying far more mass than the Sun has a much stronger gravitational squeeze at its core, which drives fusion at a dramatically higher rate, producing a brilliant, almost extravagant output of energy. You might reasonably assume that having more fuel should mean living longer, but the opposite turns out to be true. Massive stars spend their fuel recklessly, burning through it so quickly that some, shining tens of thousands of times brighter than our own sun, survive for only a few million years, a genuine blink of an eye in cosmic terms. During that brief, brilliant existence, though, they build heavier and heavier elements in layered shells inside their cores, almost like an onion assembled entirely from nuclear reactions, and their fierce outward radiation actively sculpts nearby gas clouds, sometimes even triggering entirely new waves of star formation nearby. When their cores finally can no longer support themselves, many of these massive stars end in spectacular collapse, an ending we'll return to shortly. Red dwarf stars tell almost the opposite story entirely. They are, by a wide margin, the most common type of star in the galaxy, and yet not a single one has ever had the chance to reach true old age, simply because the universe itself isn't old enough yet. Red dwarfs burn their hydrogen fuel remarkably slowly and efficiently, and their interiors stay well mixed, allowing them to access far more of their total hydrogen supply over time than larger, more wasteful stars ever manage. Because they're so cool and comparatively dim, red dwarfs may go on shining steadily for trillions of years, vastly outlasting brighter, more dramatic stars like our own sun. Long after every bright, familiar star in tonight's sky has faded into darkness, countless red dwarfs may still be quietly glowing, steady points of light scattered across an aging, increasingly empty cosmos. Many are too faint to spot with the naked eye, but they frequently host planets in remarkably close orbits, since a habitable temperature range around such a dim, cool star sits much closer in than it does around the sun. Red dwarfs are a quiet reminder that the universe holds long, patient futures, not just ancient, dramatic pasts. Some stars aren't brief fireworks at all. They're slow-burning lanterns, built to outlast almost everything else in the sky. At the opposite extreme sit the blue stars, announcing extreme surface heat through their very color, since their radiation is shifted toward shorter, bluer wavelengths, a direct signature of temperatures far higher than our own suns. These stars are often massive, intensely luminous, and visible across genuinely enormous distances, frequently dominating young star clusters with their sheer brilliance. But they never remain for long. Their cores consume fuel at a genuinely ferocious rate, and their powerful radiation drives strong stellar winds outward into surrounding space, in some cases carving visible bubbles into nearby gas clouds. Because their lifetimes are so short, blue stars usually mark regions where star formation happened relatively recently, cosmic signposts of youth scattered through a cluster. A cluster full of blazing blue stars tells astronomers, at a glance, that it simply hasn't had time to age yet. Though rare, these stars shape their environments powerfully, flooding nearby clouds with ultraviolet radiation, influencing the newborn stars around them, and often quietly setting the stage for the kind of violent, spectacular ending we're about to explore. Because here's the thing about stellar death, it was never purely destructive. Stars are, in a very real sense, the universe's element factories. Over a star's lifetime, nuclear fusion steadily builds new atomic nuclei deep inside its core. In lower mass stars, carbon and oxygen eventually get exposed and released as the star's outer layers gently drift away into space. In far more massive stars, advanced fusion stages can build elements all the way up to iron, layered carefully inside the core. Iron marks a genuine turning point, because fusing it doesn't release useful energy for the star anymore. It consumes energy instead, and once the core can no longer support itself against gravity, collapse quickly follows. The resulting explosion, a supernova, throws that entire enriched mixture of elements outward into space at tremendous speed, and that expanding debris eventually mixes with ordinary interstellar gas, becoming raw material for entirely new star systems. Later still, a rocky planet, a seashell, a tree, a human body, every single one of them ultimately requires ingredients that were first assembled inside earlier generations of stars. Stellar death was never simply an ending. It's one of the primary ways the universe recycles matter into new, increasingly complex forms, layer after layer, generation after generation, stretching back long before our own solar system ever began to take shape. Which brings us to something worth sitting with for a moment. The calcium in your bones, the iron carried through your blood, the very oxygen filling your lungs right now. None of it was born here on Earth. All of it was forged through cosmic processes that began long before our solar system existed at all, inside the fierce, patient hearts of stars, in fusion reactions running for millions or billions of years, and later, in the sudden, catastrophic violence of their deaths. Those enriched clouds of stellar debris eventually collapsed again, forming new stars, new planets, new moons, and, given enough time and the right conditions, new forms of life. Your body isn't separate from the universe we've been exploring tonight. It is, quite literally, made from material that has already passed through stellar furnaces, through ancient explosions, through slowly drifting interstellar clouds, over and over, across billions of years. The atoms that make up you have been travelers for longer than almost anything you could name, crossing the galaxy itself, long before they ever became skin, or breath, or thought, or heartbeat. Astrophysics turns this from a poetic idea into something genuinely measurable. we're not simply looking outward at the stars tonight. In the most literal sense available to physics, we are made from them. It's worth remembering, too, that our own sun's quiet, solitary existence isn't actually the galactic norm. A considerable fraction of all stars in the Milky Way, by some estimates, close to half, don't orbit alone at all. They exist instead as binary systems, two stars gravitationally bound together, orbiting a shared center of mass, sometimes separated by a distance smaller than our own solar system, sometimes stretched out across a distance far greater than the gap between the Sun and its nearest stellar neighbor. Some binary pairs orbit so closely that they physically share a common envelope of gas, gradually exchanging material back and forth, quietly shaping one another's evolution over millions of years. Others remain so widely separated that each star lives out its life almost entirely independently, only loosely bound by gravity across trillions of kilometers of empty space. This companionship can matter enormously for how a star eventually dies. We already discussed how a white dwarf can slowly steal gas from a companion star, eventually detonating as a Type I supernova, and how millisecond pulsars, in other systems, can be spun up to extraordinary speeds by gas pulled from a nearby partner. A star's fate, it turns out, often isn't determined by its own properties alone. It can depend just as much on which other star happened to form nearby, in the very same collapsing cloud, billions of years ago, and how closely the two of them ended up bound together ever since. Not every star ends its life in a dramatic core collapse explosion. Stars roughly the size of our own sun follow a gentler, quieter path, one that still leaves behind something genuinely strange. When a sun-like star finally exhausts the usable fuel in its core, it doesn't collapse into a black hole or a neutron star. Instead, it sheds its outer layers gradually into space, leaving behind a small, extraordinarily dense remnant called a white dwarf. This object is only roughly Earth-sized, and yet it can contain a large fraction of the Sun's original mass, packed into a sphere you could, in principle, fit inside a single continent. Ordinary thermal pressure isn't what holds a white dwarf up against its own crushing gravity anymore. Instead, a purely quantum mechanical effect called electron degeneracy pressure takes over, a fundamental rule of nature that simply forbids electrons from being squeezed into identical quantum states, no matter how hard gravity pushes. A white dwarf no longer generates energy through fusion in any ongoing way. It shines simply because it remains hot from its earlier life, slowly cooling across almost unimaginably long stretches of time. Some sit alone in space, quietly fading. Others orbit a companion star and can gradually draw material away from it, a detail that turns out to matter quite a lot, as we'll see shortly. Either way, these remnants aren't simply cooling ashes in some cosmic fireplace. They're dense, glowing fossils, preserving a direct physical record of stellar evolution, long after the star that made them has technically already finished living. A white dwarf doesn't vanish the moment its glow becomes too faint to notice. It simply continues losing heat into space, little by little, across timescales so enormous that the entire current age of the universe isn't old enough to produce the final result. The theoretical end state of this slow fade is called a black dwarf, a cold, completely dark stellar remnant that no longer gives off any meaningful light at all. No one has ever actually observed one, and no one ever will anytime soon, because even the oldest white dwarfs currently known simply haven't had enough time yet to cool that far. It's a genuinely strange idea to sit with. Physicists can describe, with real mathematical confidence, an object that should exist only in a future so remote that entire galaxies may look completely different by the time it finally forms. A black dwarf would be something like a memory of a star, still carrying its original mass, still obeying gravity exactly as it always did, but no longer shining at all. A quiet, patient fossil of light, waiting at the very far end of stellar evolution for a universe old enough to finally produce it. There's a very different, far more explosive fate waiting for some white dwarfs, though, one that depends entirely on whether they happen to share a close orbit with another star. If gravity slowly pulls a stream of gas away from that companion, funneling it onto the white dwarf surface over thousands or millions of years, the white dwarf's internal conditions can eventually become extreme enough to ignite carbon buried deep in its core, all at once, in a runaway thermonuclear reaction that tears through the entire star within seconds. Unlike an ordinary core collapse supernova, this kind of explosion leaves absolutely nothing dense behind. No neutron star, no black hole. The white dwarf is simply, completely unbound, its material scattered entirely into space. Astronomers call this a Type I supernova, and remarkably, because these explosions tend to detonate at very similar masses, they also reach very similar peak brightness almost every single time, which lets astronomers use them as a kind of cosmic measuring stick. Compare how bright an explosion actually was against how faint it appears from Earth, and you can calculate, with genuine precision, exactly how far away it happened, even across billions of light years. It was exactly this technique, applied to distant exploding stars in the late 1990s, that revealed something nobody expected at all. The expansion of the universe isn't gradually slowing down under its own gravity, the way everyone assumed. It's speeding up. Astronomers gave the unknown cause of that acceleration a placeholder name, dark energy, though the label describes an effect far more confidently than it explains a cause. Whatever it actually is, it currently dominates how the universe behaves on the very largest scales, even though its influence is completely overwhelmed by gravity and ordinary physics in our own everyday, local surroundings. We'll come back to this mystery a little later tonight. Massive stars, the ones that end in genuine core collapse explosions rather than the gentler white dwarf pathway, can leave behind something far stranger than any stellar ember, a neutron star. After a massive star explodes, its core can collapse into one of the strangest objects known to science. Gravity squeezes the remaining matter so fiercely that ordinary atoms are essentially shattered, their electrons and protons forced together into neutrons, producing materials so dense that ordinary comparison almost fails entirely. The object left behind may only be about the width of a modest city, and yet it can contain more mass than our entire sun. A sugar cube-sized piece of that material, if such a sample could somehow exist here on Earth, would weigh roughly as much as an entire mountain. These remnants aren't merely heavy, either. They can spin extraordinarily rapidly, hold magnetic fields more intense than almost anything else in nature, and warp the space-time around them so severely that their surface gravity can reach billions of times stronger than Earth's own. A neutron star is essentially what happens when a stellar core refuses to become a black hole, but gets compressed almost as far as physically possible without quite crossing that final line. Some of these neutron stars announce their existence through an almost impossibly precise, rhythmic sweep of radio waves. A pulsar is born when a collapsed stellar core becomes both extremely dense and rapidly spinning, its magnetic field channeling radiation into narrow, focused beams streaming outward from its magnetic poles. If one of those beams happens to sweep across Earth as the star rotates, radio telescopes detect a pulse, arriving with a regularity precise enough to rival some of the best clocks humanity has ever built. Some pulsars complete dozens of rotations every single second, their timing steady enough that astronomers use them to test gravity itself, map faint interstellar gas, and search for the tiniest disturbances caused by passing gravitational waves. The pulsing itself doesn't mean the star is literally flashing on and off. It means a narrow beam is simply sweeping past our particular line of sight as the object spins. In space, orientation alone can decide whether something appears completely silent or spectacularly, rhythmically loud. A pulsar might have been sending its beams outward for millions of years, and only the world sitting in exactly the right direction ever notice its rhythm at all. Among neutron stars, a rare and genuinely extreme subgroup takes this already extreme family even further: magnetars, whose magnetic fields can reach roughly 1,000 trillion times stronger than Earth's own. Near a magnetar's surface, ordinary atoms would be stretched and warped by magnetic forces beyond anything remotely familiar, distorted into shapes that simply don't occur anywhere else in nature. These objects can unleash sudden, violent eruptions called starquakes, where the neutron star's extraordinarily rigid crust suddenly shifts under accumulated magnetic stress, releasing a burst of X-rays and gamma rays powerful enough to be detected across enormous cosmic distances. In one documented case, a magnetar flare from deep within our own galaxy was strong enough to measurably affect Earth's upper atmosphere, despite originating from a source many thousands of light years away. Magnetars are a vivid reminder that the universe doesn't just use familiar forces, it magnifies them, sometimes to a scale that becomes almost unrecognizable, taking something as ordinary as magnetism and turning it into an engine capable of reshaping matter and releasing energy with genuinely stunning violence. When two neutron stars finally spiral together and collide, the resulting event is more than simply a gravitational spectacle. It's a genuine cosmic foundry. These stars contain matter packed so tightly that their final collision throws intensely neutron-rich debris outward at incredible speed, and in that expanding material, atomic nuclei can rapidly capture neutrons, building heavy elements that ordinary stellar fusion simply cannot produce on its own. This rapid process can forge gold, platinum, uranium, and a whole range of other rare, heavy elements, all in the space of moments. When astronomers finally observed one of these mergers directly, they watched a fading glow called a kilonova, whose changing color and behavior matched, almost perfectly, the theoretical signature of heavy element production in real time. It was a powerful, direct confirmation that some of Earth's most treasured metals may genuinely trace their origin back to a collision between two dead stars. Every gold ring, every platinum instrument, every trace of certain rare heavy elements scattered through the crust of our planet may carry a history stranger and older than any human mind could ever produce, beginning instead in a single, brilliant flash where two stellar remnants finally became one, scattering treasure outward across the galaxy in the process. Light isn't the only messenger capable of carrying news of an event this violent across the universe. Some of the most dramatic events happen almost entirely in darkness, hidden by distance, by dust, or simply by the nature of the objects involved. Gravitational wave observatories give scientists an entirely different way to detect them. These instruments don't record sound moving through air, since space has no air to carry it. Instead, they measure tiny, precise changes caused when space-time itself gets squeezed and stretched by a passing wave. Researchers often convert these signals into audio, letting them genuinely hear a rising chirp as two compact objects spiral together in their final moments, a pattern that reveals their masses, their spins, and the sheer violence of their final collision. It's a little like listening to a locked, distant room through the walls of reality itself. Telescopes reveal the universe through light. Gravitational wave detectors reveal the motion hidden underneath in the fabric of space-time. Together, they've turned astrophysics into a genuinely richer story, one where some events are seen, some are heard, and some are only truly understood once both kinds of messages finally arrive together. Let's sit with black holes properly now, because the name itself can be a little misleading. A black hole isn't a tunnel punched into some cosmic floor, and it isn't simply empty space either. It's a region where mass has curved space-time so severely that every possible future path, in every direction, leads deeper inward. The darkness comes from a very specific fact. Light cannot escape once it crosses a certain boundary. Outside that boundary, gravity still behaves in a way that follows perfectly ordinary rules. A planet could orbit a black hole indefinitely and safely, provided it kept a respectful distance. The genuinely strange part isn't that a black hole acts like some cosmic vacuum cleaner, hungrily swallowing everything nearby. The strange part is that geometry itself becomes a trap. Paths that would normally lead an object safely back outward simply bend toward the center instead. Space and time, under conditions this extreme, stop being a passive backdrop and become, quite literally, the architecture of captivity. A black hole isn't emptiness. It's the shape of no return. That boundary has a name, the event horizon. It isn't made of fire or metal or any solid material whatsoever. It's simply a point of commitment. Outside it, a sufficiently powerful rocket could, in principle, still escape. Inside it, no signal of any kind can ever travel back out to the wider universe again. The boundary earns its name precisely because events occurring within it can never influence outside observers, at least not by sending light or any other ordinary information outward. For an especially massive black hole, crossing that horizon might not even feel dramatic in the moment. There's no physical wall to bump into, no sudden jolt. And yet the meaning of that crossing is absolute. Afterward, quite literally every possible route through space-time points inward, with no exceptions. The event horizon separates the knowable from the permanently unknowable, giving astrophysics a genuinely rare kind of natural border, not an edge of matter, but an edge of communication itself. We can study everything happening around it, in exquisite detail, using telescopes and simulations. What happens beyond it remains hidden behind what might be the strictest curtain the universe has ever drawn. Nothing that crosses this boundary ever escapes again, and the reason runs deeper than simple speed. You might imagine that a sufficiently powerful engine could just climb back out, the way a rocket escapes Earth's gravity. But inside the event horizon, the very concept of outward stops working the way it does everywhere else. Space-time's geometry tilts so completely that every future direction, without exception, leads further in. Light, which travels at the fastest possible speed the universe allows, cannot find any path back out. And since nothing can travel faster than light, everything else is trapped right along with it. This is precisely why the event horizon matters so much. It doesn't merely mark a region where gravity happens to be very strong. It marks the exact point where escape becomes physically, mathematically impossible. Whatever falls through, gas, dust, an entire star, radiation itself, simply cannot report back on its journey afterward. To outside observers, only a few indirect clues remain. The resulting black hole's mass, spin, an electric charge can still shape its exterior in measurable ways. But the specific details of whatever actually fell in are hidden completely from view, leaving behind a mathematically precise boundary wrapped around a profound, permanent mystery. Rotation changes this story considerably. A spinning black hole doesn't simply sit in space-time like a still weight resting on a stretched sheet. It actively twists the surrounding fabric of space as it turns, an effect called frame dragging, which means nearby space itself gets dragged along in the direction of rotation. Close enough to a spinning black hole, an object literally cannot remain perfectly still relative to the distant universe. It's forced to share in that rotational motion, whether it wants to or not. Around a rotating black hole, there's a region just outside the event horizon called the ergosphere, where this dragging becomes completely unavoidable. In theory, energy can even be extracted from this region, almost as though the black hole's own spin were functioning as a kind of cosmic battery. Some researchers believe this process may help power the enormous jets seen streaming from certain active galactic centers. Spin transforms a black hole from a simple, static trap into something closer to a dynamic engine. It doesn't merely curve spacetime passively. It can twist it, stir it, and actively shape how nearby matter behaves. Classically, black holes seemed like they should be perfectly, permanently dark, incapable of emitting anything at all. Quantum physics complicated that picture considerably. In the 1970s, the physicist Stephen Hawking combined ideas from gravity, thermodynamics, and quantum theory to show that black holes should, in principle, emit a faint form of radiation after all. This radiation doesn't come from matter somehow escaping back out from within the event horizon itself. It arises instead from subtle quantum effects occurring right at the boundary, where the mere presence of an event horizon changes what empty space itself is actually capable of doing. The smaller a black hole is, the warmer, and the more actively radiating, this effect should become. Large astrophysical black holes, the kind actually found in the universe, radiate so weakly through this process that the effect remains far beyond anything we could currently detect. Even so, the underlying idea is genuinely profound. It suggests that black holes carry a real, physical temperature, a real entropy, and a slow, patient path toward eventual evaporation, one that raises deep, still unresolved puzzles about information and the fundamental foundations of physics. A black hole, it turns out, may not be an eternal prison after all. It may simply be an extraordinarily slow process, patiently, quietly returning its captured energy back to the universe, over a timescale almost too long to meaningfully imagine. In 2019, scientists released the very first direct image of a black hole's immediate surroundings, and at first glance, the picture looked almost deceptively simple, a dark central void surrounded by a lopsided, glowing orange ring. Behind that single image, though, sat a planet-wide network of radio observatories, all working together as one enormous virtual telescope called the Event Horizon Telescope. Their target was the supermassive black hole at the center of a galaxy called Messier 87. The glowing ring in the image showed radiation from superheated material orbiting near the event horizon, its light bent and shaped by gravity so intense that it visibly curved around the black hole itself. The dark region at the center wasn't the black hole photographed directly, in any ordinary sense. It was its shadow, created by light being captured and by paths bending around the horizon in exactly the way general relativity had long predicted. This was a genuine triumph, because black holes had, for decades, only ever been studied through indirect evidence. At last, their immediate surroundings had been resolved in real, visual detail, giving the world visual proof of one of gravity's strangest predictions, not as an artist's imaginative rendering, but as actual data, turned into something you could genuinely look at. Our own galaxy holds a much quieter version of this same phenomenon at its very center. At the heart of the Milky Way sits a compact object containing millions of times the mass of our Sun, difficult to observe directly because thick dust and gas block visible light along the galactic plane. Astronomers uncovered it indirectly by carefully watching ordinary stars whip around an apparently empty point in space at extraordinary speeds, their orbits revealing a massive, invisible object packed into a region far too small to be anything remotely ordinary. Compared to some far more active galactic centers, ours is relatively calm. It isn't currently blazing as a brilliant quasar. Instead, it flickers and occasionally flares as small amounts of material drift close enough to fall toward it. This relative calm is fortunate for life out here in the galaxy's quieter suburbs, where our solar system happens to orbit comfortably far from the core. Sagittarius A*, as astronomers call it, is a hidden anchor, quietly shaping the motion of nearby stars and offering researchers a natural laboratory for studying gravity at its most extreme, right in our own cosmic backyard. Before any material actually crosses a black hole's event horizon, it typically gathers first into a rapidly rotating disk. Friction, turbulence, magnetic fields, and sheer compression heat this infalling gas to genuinely extreme temperatures, and depending on the specific system, that glowing disk can shine brilliantly in visible light, ultraviolet, or X-rays. Around stellar mass black holes, this material is often pulled directly from a nearby companion star. Around galactic centers, the fuel might come from drifting gas clouds, disrupted stars, or long streams of interstellar material. Crucially, none of this light actually comes from inside the black hole itself. It comes from matter outside, during its final, doomed struggle against overwhelming gravity. This is precisely why black holes can end up associated with some of the most brilliant sources in the entire universe, even though the holes themselves remain completely dark. The surrounding environment becomes the lamp. The closer material moves toward the horizon, the more efficiently gravitational energy gets converted into radiation, in some cases more efficiently than even ordinary nuclear fusion ever manages. Darkness, in a genuinely strange twist, can end up surrounded by some of the most intense light the universe is capable of producing. Occasionally, that darkness reveals itself in a far more violent, one-time way. If an ordinary star wanders too close to a massive black hole, gravity pulls noticeably more strongly on the near side of the star than on the far side. That difference can stretch the star until it's genuinely torn apart, an event astronomers call a tidal disruption, sometimes nicknamed spaghettification for the long, glowing threads of stellar material it produces. Some of that shredded material gets flung outward, while some falls back and forms a bright, superheated flow swirling around the black hole. Astronomers detect these events as sudden, dramatic flares from galactic centers that had previously appeared completely quiet, flares that can last for months, sometimes years, revealing exactly how a black hole feeds whenever chance happens to deliver a star close enough. The process is genuinely violent, but scientifically invaluable too, exposing ordinary matter under conditions of extreme gravity and briefly illuminating regions that might otherwise remain permanently unseen. Let's pause here for a moment. If you've been drifting in and out of focus, that's exactly what these long, quiet science journeys are meant to do for you. There's no need to hold on to every detail we've covered so far: the bending of time, the forging of gold inside dying stars, the shape of a trap made from nothing but geometry. Just let it settle over you gently, the way starlight settles over a quiet field at night, without asking anything of you at all. We still have some distance left to travel tonight, out toward the invisible architecture holding entire galaxies together, and back toward the very first stars that ever lit the darkness. There's no rush. Just stay resting here, and let the rest of the journey carry you the remaining distance. Einstein's own theory predicted something that seemed almost too strange to be real, that gravity itself could bend light. Before general relativity, gravity was usually imagined simply as a force acting directly between two masses. Einstein described it very differently. Mass and energy curve spacetime, and light, traveling along whatever path spacetime actually offers it, follows the resulting curve. During a solar eclipse in 1919, astronomers carefully measured starlight passing near the sun and found that the apparent positions of distant stars had genuinely shifted, exactly as Einstein's equations predicted. That single result made Einstein famous almost overnight and changed physics permanently. The bending itself was small, but its meaning was enormous. Light has no rest mass at all, and yet its path responded to gravity anyway, because gravity doesn't pull on light directly. It shapes the very road light is traveling along. Today, this effect sits at the center of a great deal of modern astrophysics. It helps reveal hidden mass, tests relativity under real cosmic conditions, and lets astronomers study objects otherwise far too distant or too faint to examine at all. There's a certain quiet elegance to the whole idea. A beam of light believes, the entire time, that it's traveling in a perfectly straight line. It's simply the universe around it that has been quietly, invisibly curved. When a massive galaxy, or an entire galaxy cluster, happens to sit directly between Earth and some more distant object, its gravity can act almost like a natural telescope. Light from that distant background source bends as it passes around the foreground mass, sometimes forming long, curved arcs, sometimes splitting a single distant object into several separate images, all visible simultaneously around the lensing galaxy or cluster. This magnification effect, called gravitational lensing, has revealed galaxies that would otherwise be far too faint to study at all. Some of the most distant known galaxies in the universe have been found specifically with the help of this fortunate cosmic magnification. The foreground object doesn't need any polished glass or mirrors of its own. Its mass alone does all the work, curving space-time and bending the light that happens to pass nearby. Lensing can also distort background images in ways that let astronomers directly map the distribution of mass, including invisible dark matter, throughout the foreground structure. In rare, especially precise alignments, the result becomes almost startlingly elegant, a complete, glowing ring of light encircling the lensing object entirely, called an Einstein ring. More often, the effect appears more subtly, as gently stretched smears of impossibly ancient light. Either way, the universe becomes, quite literally, its own instrument, using gravity itself to bring hidden depths into view that no telescope built by human hands could ever reach alone. That phrase, dark matter, sounds mysterious because it genuinely is. It doesn't announce itself through brightness, through color, or through any recognizable chemical fingerprint. Instead, it's inferred entirely from motion, from structure, and from its gravitational effects on everything around it. Stars orbit their galaxies far too quickly to be explained by the visible matter alone. Galaxy clusters hold together with considerably more gravitational pull than their visible matter could ever provide. Light from distant background objects bends as though extra, unseen material were sitting directly in its path. Every one of these clues points toward the same conclusion. Something out there responds to gravity, but barely interacts with light or any other form of electromagnetic radiation at all. This makes dark matter genuinely difficult to identify directly. It cannot simply be photographed, and it doesn't behave like ordinary gas or dust in any familiar way. And yet, it appears to be considerably more abundant, several times more abundant, than all the ordinary matter that makes up stars, planets, and people combined. Scientists have proposed several possible particle candidates over the years, but none has ever been confirmed. What's remarkable is that this particular kind of ignorance isn't empty at all. It's precise. We can measure, with real confidence, exactly what dark matter does, even while the deeper question of what it actually is remains genuinely, stubbornly open. Entire galaxy clusters, remarkably, function almost like cosmic scales for weighing this invisible material. A galaxy cluster can contain hundreds or even thousands of individual galaxies, along with hot, X-ray emitting gas, all bound together by gravity. To measure a cluster's total mass, astronomers don't need to gather it up piece by piece. They can instead study how quickly its individual galaxies are moving, measure the temperature of its hot gas, or observe exactly how strongly the cluster bends background light. All three methods, remarkably, tend to agree, and all three consistently point toward far more total mass than the visible galaxies alone could ever provide. In some particularly famous cases, astronomers have observed colliding galaxy clusters where ordinary, visible matter gets visibly slowed down and displaced by the collision itself, while the gravitational lensing signal, tracing the underlying dark matter, sails straight through the collision almost completely undisturbed. This offers some of the strongest available evidence that dark matter isn't simply some accounting error in how we count stars, but a genuinely separate kind of material, behaving in genuinely different ways from the ordinary matter we're familiar with. Two researchers deserve particular credit for uncovering different pieces of this puzzle. Working with photographic plates at the Harvard College Observatory in the early 20th century, an astronomer named Henrietta Leavitt studied variable stars inside the Magellanic Clouds and noticed something remarkable. Certain variable stars with longer pulsation periods were consistently, measurably brighter than those with shorter periods. This period-luminosity relationship became one of the single most important tools in the entire history of astronomy, eventually allowing other researchers to measure cosmic distances far beyond the reach of any earlier method. Leavitt didn't receive anywhere near the recognition her discovery deserved during her own lifetime, and yet modern cosmology rests, in no small part, directly on her careful, patient measurements. It's a genuinely powerful story, one that shows how patient attention to a repeating pattern can quietly reshape humanity's entire understanding of its place in the cosmos. A woman, carefully examining glass photographic plates, found a rhythm hidden in distant starlight, and that rhythm ended up opening the true scale of the universe. Decades later, the astronomer Vera Rubin studied how stars and gas actually move within spiral galaxies and found something genuinely strange. The expectation, based purely on visible matter, was that material farther from a galaxy's center should orbit noticeably more slowly than material closer in. Instead, rotation curves consistently stayed surprisingly flat. Stars in the outer regions of these galaxies were moving far too quickly to be explained by the visible light alone. Rubin's careful, painstaking observations, combined with related work from other researchers, strengthened the growing case that galaxies must contain enormous amounts of unseen mass. Her measurements didn't identify exactly what that hidden matter actually was, but they made an overwhelmingly persuasive case that something important was genuinely missing from the visible picture entirely. This work helped transform dark matter from a minor scientific curiosity into one of the central, defining problems in modern astrophysics. Rubin's legacy extends well beyond a single discovery about spiral galaxies. It's a reminder that the universe often reveals its deepest secrets through motion alone. Stars quietly orbiting the outskirts of distant galaxies had been telling a story the entire time, and she simply listened closely enough to finally hear it. We touched briefly earlier on how distant, exploding stars first revealed that the universe's expansion is accelerating rather than slowing down, but it's worth sitting with just how unsettling that discovery actually turned out to be. The majority of the universe's total energy budget appears to exist in a form whose fundamental nature remains genuinely unknown. It isn't dark matter, since it doesn't gather into halos around individual galaxies the way dark matter does. It seems smooth, persistent, and directly connected to the ongoing expansion of space itself. One possibility is something called the cosmological constant, a term Einstein originally introduced into his own equations for entirely different reasons, decades before this discovery. Another possibility involves some kind of dynamic, evolving field, sometimes called quintessence. There are even more radical ideas suggesting that gravity itself might behave subtly differently across the very largest cosmic distances. Each explanation carries its own consequences, and each must eventually survive careful observation. Measurements of distant supernovae, the cosmic microwave background, the large-scale clustering of galaxies, and gravitational lensing all help researchers narrow down the possibilities. And yet the central mystery remains stubbornly open. Dark energy isn't some small, forgivable missing detail in our understanding. It's a genuine signal that our best current picture of physical reality may still be fundamentally incomplete at the largest scales the universe has to offer. On the very grandest scales imaginable, the universe isn't arranged randomly at all. Galaxies gather along enormous strands, sprawling walls, and dense knots of matter, separated by vast, comparatively empty voids. This entire structure grew from tiny density differences present in the extremely early universe, gradually amplified over billions of years by the patient, steady pull of gravity. Dark matter formed the underlying gravitational scaffolding for all of this, while ordinary gas fell into that same pattern, eventually collapsing to form the stars and galaxies we can actually observe. Astronomers call the resulting large-scale pattern the cosmic web. Galaxy clusters sit at its densest intersections, almost like cities gathered at busy crossroads, while thinner filaments of galaxies stretch across hundreds of millions of light years in between. Researchers map this entire structure by carefully measuring galaxy positions and by studying how the light of distant quasars gets absorbed as it passes through intervening gas along the way. The cosmic web reveals that the universe genuinely has a texture to it. It isn't merely a random scatter of isolated galaxies floating in emptiness. It's connected quietly and pervasively by gravity into a vast architecture where even the largest visible structures trace directly back to minute ripples present in the earliest moments of the cosmos. Between the dense filaments of that cosmic web lie enormous regions containing relatively few galaxies at all, sometimes stretching for tens or even hundreds of millions of light years. These cosmic voids aren't perfectly empty. Stray gas, faint galaxies, dark matter, and background radiation still exist scattered within them. But compared to the crowded filaments and dense clusters nearby, they are, by any reasonable measure, genuine cosmic deserts. Their existence helps scientists understand exactly how the universe's large-scale structure actually formed in the first place. Matter flowed steadily away from underdense regions and gathered instead where gravity had a stronger grip, making already empty places emptier still, and already crowded places more crowded over time. Voids are also genuinely useful for testing cosmological models, since their exact shapes and growth rates depend sensitively on gravity, dark matter, and dark energy working together. There's something quietly haunting about their sheer scale. A spacecraft traveling directly through the heart of one of these voids would see remarkably little change around it, for far longer than the entire span of recorded human history could comfortably measure. These vast, empty spaces are a reminder that the universe isn't only filled with wonders. It also contains absences large enough to become wonders entirely in their own right. Galaxies themselves are rarely finished, static objects. A galaxy's overall shape and history are often built directly from countless collisions and quiet acts of gravitational capture over billions of years. Smaller galaxies fall into larger ones and get stretched by tidal forces until their stars are pulled into long, glowing streams scattered across the larger galaxy's halo. Gas clouds get pulled inward, stirred, compressed, and sometimes triggered directly into forming brand new stars. Over billions of years, this ongoing process gradually reshapes a galaxy's structure, size, chemistry, and internal motion. Some of the largest elliptical galaxies observed today may actually be the end product of repeated mergers, where once elegant spiral structures were slowly scrambled into more rounded, chaotic swarms of stars. Even relatively calm, undisturbed-looking galaxies often carry faint evidence of past meals, visible as subtle arcs and shells of stars surrounding them. This entire process unfolds slowly by any human measure of time, but relentlessly by cosmic standards. Gravity, it turns out, is remarkably patient. It steadily pulls neighboring galaxies together and rearranges them, over billions of years, into ever larger systems. Our own Milky Way is very much part of this ongoing story. It isn't simply a peaceful, isolated spiral floating alone through space. Smaller companion galaxies orbit around it, and some of them are actively being torn apart by its gravity, right now, tonight. The Sagittarius dwarf galaxy offers one of the clearest examples available. As it loops repeatedly around the Milky Way, tidal forces strip stars away from it, leaving behind long, glowing streams that wrap gracefully through our galaxy's halo. These stellar streams function almost like forensic evidence scattered across the sky, allowing astronomers to carefully reconstruct the path of a smaller galaxy that's slowly, steadily being dismantled. Other faint companion galaxies may be losing material in exactly the same way, gradually adding their own stars to the Milky Way's outer regions. Our galaxy, in other words, is still very much under construction. Some of the stars visible in tonight's sky may well have formed originally in an entirely different, smaller galaxy, with its own separate history, long before eventually being folded into our own. There's a much larger, more distant merger already quietly on its way. Most distant galaxies recede from us as space itself expands, but nearby galaxies can still be governed primarily by local gravity instead. Andromeda, our largest neighboring spiral galaxy, is part of the same small cluster of galaxies we belong to, and it's genuinely approaching us across intergalactic space right now. Several billion years from now, our two great spiral galaxies are expected to begin merging together. The event won't resemble an ordinary collision in any conventional sense. Stars are so widely spaced within each galaxy that direct impacts between individual stars will remain extraordinarily unlikely, exactly as we discussed earlier. The galaxies themselves, however, will be genuinely transformed. Their disks will distort dramatically, long streams of stars will arc outward into space, and compressed gas may trigger entirely new bursts of star formation throughout the encounter. Over time, the two systems may gradually settle into one larger, differently shaped galaxy entirely. Earth, by then, will likely look nothing like it does today, since our own sun will have changed dramatically over that same span of time. Still, the prediction itself remains genuinely remarkable. The night sky already contains a future encounter quietly on its way, visible tonight, if you know exactly where to look, as nothing more than a faint, unassuming smudge of light to the naked eye. Deep inside the Milky Way's halo, orbiting far outside the thin, familiar disk where most new star formation happens, sit compact swarms of stars called globular clusters, some containing hundreds of thousands of individual stars packed into a roughly spherical shape. Their stars are often extremely ancient and notably poor in heavy elements, suggesting they formed very early in the galaxy's history, before many generations of earlier stars had lived, enriched their surroundings, and died. Through a telescope, globular clusters look like glittering spheres, dense toward the center and gradually fading outward toward the edges. Inside them, stellar encounters happen considerably more often than in the far more spacious neighborhood surrounding our own sun, occasionally producing unusual objects like blue stragglers, stars that appear younger or more massive than the rest of their surrounding cluster would otherwise suggest. These clusters are genuinely valuable to astronomers because their stars all share a common origin, making them natural laboratories for studying stellar aging in a carefully controlled setting. In a very real sense, they're also time capsules. Studying a globular cluster means examining surviving fragments of the Milky Way's earliest assembly, still quietly orbiting, entirely intact, after billions of years. Not every star cluster is quite this ancient or quite this densely packed, though. Scattered throughout the Milky Way's spiral arms, considerably younger, looser groupings called open clusters mark regions where stars formed together relatively recently, from the very same collapsing cloud of gas and dust. Unlike the tightly bound, roughly spherical shape of a globular cluster, an open cluster is held together comparatively loosely, its stars gradually drifting apart from one another over tens or hundreds of millions of years as the gravity of the wider galaxy slowly pulls the group apart. The Pleiades, visible to the naked eye on a clear night as a small, tight knot of bluish stars, is one of the more famous nearby examples, its stars still young enough to appear bright and hot, still loosely wrapped in faint wisps of the very gas cloud that gave birth to them. Our own sun, remarkably, is thought to have formed inside a similar open cluster, roughly 4.5 billion years ago, surrounded by hundreds or even thousands of sibling stars. Over the enormous span of time since then, that original cluster has completely dispersed, its stars scattered individually throughout the galaxy, carried apart by countless gentle gravitational interactions along the way. Somewhere out there, scattered among the billions of other stars in the Milky Way, some of the sun's actual, original siblings may still be quietly shining tonight, utterly unrecognizable now, and probably impossible to ever specifically identify, but connected to our own star by a shared birth, billions of years ago, inside a cloud that no longer exists in any recognizable form at all. Let's travel back now, further than almost anything we've discussed so far, to a universe that hadn't yet built a single galaxy, or a single planet, or even a single ordinary star. In astronomy, the earliest generations of stars were built almost entirely from hydrogen and helium, since heavier elements simply hadn't been forged yet in any meaningful quantity. This makes truly ancient stars, the rare survivors from that early era, extraordinarily valuable. Their chemistry works almost like a fossil record, preserved directly in light. When astronomers split a star's light into a detailed spectrum, they can identify exactly which elements are present in its outer atmosphere. Some stars contain only the barest traces of iron, carbon, or oxygen, compared to our own Sun, telling astronomers that these particular stars must have formed before many earlier generations of stars had lived and died. These ancient stars are often found scattered through the Milky Way's halo, moving along unusual orbits that may still remember the galaxy's earliest, most formative assembly. They are faint, patient witnesses from a time long before rocky planets were common anywhere in the universe. Studying them is a little like reading the very first chapters of cosmic chemistry, where each missing ingredient becomes meaningful evidence of just how young and chemically simple the early cosmos really was. There's a small, almost charming quirk of scientific language worth pausing on here. Astronomers refer to every single element heavier than helium as a metal, a definition that can sound strange at first, since oxygen, carbon, and neon aren't exactly metals in everyday conversation. But astrophysics simply uses a different shorthand. The earliest universe was dominated almost entirely by hydrogen and helium, with only a small trace of lithium mixed in. Nearly everything heavier than that was built later, inside stars, inside stellar explosions, and inside violent compact object collisions like the neutron-star mergers we discussed earlier. So astronomers group all of those heavier ingredients together under this single, convenient label, using it to describe how chemically enriched a particular star, galaxy, or gas cloud has become over cosmic time. A metal-rich star likely formed from material that had already been processed by earlier generations of stars. A metal-poor star formed from a more primitive, less processed mixture. This single word ends up carrying an entire quiet history of creation, death, and recycling within it. It tells scientists whether a given cloud of gas has been touched by earlier stars, and whether it might plausibly contain the raw ingredients needed to eventually build rocky worlds of its own. In this particular language, metallicity isn't really about shine at all. It's about memory. Before planets, before dust, before anything resembling the familiar galaxies we see tonight, gravity gathered the very simplest available gas into the earliest stellar fires the universe ever produced. These hypothetical objects are often called population 3 stars, although not a single confirmed example has ever actually been directly observed. Theoretical models suggest they may have been far more massive than most stars forming today, precisely because the original primordial gas lacked the heavier elements that normally help gas clouds cool efficiently and fragment into smaller, more manageable pieces. Without that efficient cooling, larger clumps of gas could collapse all at once, creating enormous stars with genuinely ferocious cores. Their lives would have been extraordinarily brief, perhaps only a few million years, but their impact on the surrounding universe would have been enormous. These first stars produced the very first heavy elements ever to exist and flooded their surroundings with intense, energetic radiation. Some may have ended in unusually powerful explosions, scattering fresh chemistry outward into space. Others may have collapsed directly into black holes, planting the earliest possible seeds for later cosmic growth. These first stars weren't simply lights switching on somewhere in the darkness. They were the opening furnaces that began quietly changing the chemical character of absolutely everything that followed them for the rest of cosmic history. No confirmed first-generation star has ever actually been found, and the search remains difficult, since the earliest stars likely lived quickly and died long, long ago. If any unusually low-mass examples somehow managed to survive all this time, they would be incredibly rare and incredibly faint. Astronomers search for them by hunting for stars with almost no heavy elements at all, anywhere in their spectrum. Such a discovery would be genuinely extraordinary, since it would offer a direct, physical sample of matter formed from the universe's original ingredients, largely untouched since the very beginning. So far, researchers have located extremely metal-poor stars, but not yet a single one that can be confidently called completely pristine. For now, the first generation of stars remains a genuinely missing population. We know, with real confidence, that they must have existed, since later cosmic chemistry simply requires them to have come first. And yet their direct light has never been securely, unambiguously caught. It might seem strange that space contains dust at all, given how empty it generally is. Between the stars, ordinary matter is spread astonishingly thin, and yet tiny solid grains genuinely do drift there, made of carbon compounds, silicates, various metals, and icy coatings. Many of them created when aging stars shed their outer layers gently into space, or when violent explosions throw newly forged material outward at tremendous speed. Once released, that dust becomes surprisingly important. It helps cool nearby gas clouds, shields fragile molecules from harsh radiation, and provides tiny surfaces where more complex chemistry can gradually build up over time. It also physically blocks visible light, hiding entire regions that only infrared telescopes can properly reveal. In photographs of nebulae and distant galaxies, those familiar dark lanes crossing through glowing clouds are usually dust, quietly absorbing the starlight behind it. The very same kind of material eventually becomes part of new planets, comets, and moons. A single speck of interstellar dust might be tiny, but it carries an enormous history within it. The genuine ash of long-dead stars, the seed of entirely new worlds, and a quiet, patient participant in the ongoing project of cosmic construction. Some nebulae are beautiful precisely because they're genuinely active. Inside cold clouds of gas and dust, gravity can gradually begin pulling material into denser and denser pockets. The process is slow, uneven, and shaped by turbulence, magnetic fields, radiation, and passing shock waves, all working together to determine which regions eventually collapse and which simply disperse back into the surrounding cloud. In places like the Orion Nebula, young stars have already ignited inside a glowing environment made almost entirely of leftover gas, their radiation lighting up the surrounding cloud and sculpting it into dramatic ridges, hollow cavities, and towering pillars. Nearby, still denser knots of material may be quietly preparing to form even more stars in the future. A nebula isn't merely a beautiful, painted backdrop hanging in space. It can be a genuinely active, working environment where raw material is actively becoming stellar architecture. Some of the cloud will eventually collapse into new stars. Some will simply get blown away entirely, and some may gather, later, into rotating disks where entirely new planets can begin to form. A star's earliest stage of life is hidden deep inside a dense clump of gas and dust, cold enough for molecules like hydrogen and carbon monoxide to survive intact. In certain regions, gravity finally overcomes the surrounding internal pressure, and as material falls inward, it heats up, forming a growing, central object. This isn't yet a true star, since sustained hydrogen fusion hasn't ignited at its core. It's called a protostar, still wrapped in a thick, opaque envelope that blocks most visible light entirely, which is why infrared and radio telescopes are usually needed to study these hidden beginnings properly. Jets of material can shoot outward from the protostar's poles, while a rotating disk gradually forms around its equator, continuously feeding new material inward. The whole process looks genuinely messy, with infalling gas, energetic outflows, ongoing rotation, and tangled magnetic fields all working together simultaneously. Over time, if the growing object gathers enough total mass, its core finally becomes hot and dense enough to ignite sustained fusion. What began as nothing more than a cold, quiet pocket inside a dark, drifting cloud finally becomes a genuinely new source of starlight. As a young star gathers mass, whatever material is left over often flattens naturally into a rotating disk surrounding it, simply because the original cloud carried some inherent spin, which becomes increasingly important as everything collapses inward together. Inside that disk, individual dust grains collide and gradually stick together. Larger clumps form over time, then planetesimals, then genuine protoplanets, eventually large enough to clear distinct paths through the surrounding gas and leftover debris entirely. Close to the newborn star, intense heat favors the formation of rock and metal worlds. Farther out, ice can survive intact, making larger cores and eventually gas giant planets, considerably more likely to form. Astronomers have directly imaged disks around other young stars showing rings, gaps, and spiral patterns that may reveal planets actively forming or gently disturbing the surrounding material as they grow. Our own solar system almost certainly began this exact way, which strongly suggests that planets are a natural, expected byproduct of ordinary star birth, rather than some rare, unlikely accident. A disk surrounding a newborn star functions much like a genuine construction zone, containing all the raw ingredients needed for future worlds, moons, asteroids, comets, and, given enough time and the right conditions, eventually places where chemistry itself might become life. A young planetary system, though, is rarely stable and tidy from the very beginning. While still embedded within its birth disk, a planet's orbit can shift considerably inward or outward through ongoing gravitational interactions with the surrounding gas. Later, close encounters with neighboring planets can scatter entire worlds into completely new orbits. This kind of planetary migration explains why some giant planets have been found sitting extremely close to their host stars, even though they most likely formed much farther out, where icy material was originally abundant enough to build them. Migration can genuinely reshape an entire planetary system, potentially delivering icy material toward inner rocky worlds, disturbing asteroid belts, or flinging smaller planets out into interstellar space entirely. Even within our own solar system, considerable evidence suggests the giant planets shifted position significantly early in their history, directly influencing how the smaller bodies that remain today ended up arranged. A planet's current orbit isn't some kind of fixed birth certificate. It's a history, quite literally written by gravity, and a planet's present path may simply be the end result of drifting, colliding, and surviving through a genuinely crowded, chaotic youth. Some of the resulting planets discovered around other stars genuinely shocked astronomers when they were first found. A giant planet like Jupiter was generally expected to form far from its star, where cold conditions allow large cores and thick atmospheres to gather comfortably. And yet so-called hot Jupiters circle remarkably close to their host stars, sometimes completing an entire orbit in just a few Earth days. Their atmospheres get blasted continuously by intense stellar radiation, and some end up considerably more inflated than models originally predicted. Because they're massive and orbit so close, hot Jupiters were actually among the easiest exoplanets to detect using both stellar wobble measurements and transit observations. Their existence forced scientists to seriously rethink planetary formation and migration together. Many of these worlds probably began their existence much farther from their star, and only later migrated inward through ongoing interactions with their birth disk or through gravitational encounters with other planets in the same system. Their presence can genuinely disrupt smaller, more fragile planets nearby, reshaping the entire architecture of a system in the process. Some exoplanets discovered so far push the very definition of ordinary weather in genuinely strange directions. One famous example is a scorching blue gas giant whose atmosphere contains fine silicate particles, the same broad family of material found in ordinary glass and rock here on Earth. This particular planet orbits so close to its star that temperatures soar and fierce winds race continuously around the entire globe. Under these extreme conditions, silicate material can condense into tiny droplets or grains and fall, quite literally, through the atmosphere. Though calling it gentle rainfall would be misleading, the planet's ferocious winds likely drive these falling particles sideways at extreme speeds, creating a weather system genuinely unlike anything found anywhere on Earth. The planet's distinctive blue color doesn't come from any ocean at all. It comes instead from light scattering off haze suspended in its scorching atmosphere. Exoplanet weather has become a genuine, active field of science, since telescopes can now study starlight passing through or reflecting off these distant atmospheres directly. From that light alone, astronomers can infer temperature, chemical composition, cloud coverage, and even large-scale atmospheric circulation. The result is genuinely astonishing. Weather, it turns out, isn't limited to water and air. On other worlds, it can be made of glass, of metal, and of pure, relentless heat. Other distant worlds may hold entire oceans deeper than Earth's own mantle. Some planets appear to contain far more water than Earth does, arranged not as scattered seas across separate continents, but as a single, continuous global layer, hundreds or even thousands of kilometers deep. Pressure at the bottom of an ocean that deep would become genuinely enormous. At sufficient depth, water itself might transform into an exotic, high-pressure form of ice, even while the layers above it remain fully liquid. This ice wouldn't be cold in any ordinary sense. It would be created entirely by crushing pressure rather than by low temperature. Worlds like this raise genuinely fascinating questions about habitability. On Earth, ocean water interacts directly with rock through the seafloor, exchanging chemicals that matter enormously for life as we understand it. If a deep-water world has a layer of high-pressure ice completely separating its ocean from the rocky interior below, that crucial chemical connection could be severely limited or entirely cut off. And yet internal heat, dissolved minerals, and unusual ocean layering might still create other possibilities we haven't fully considered yet. These strange, water-heavy worlds genuinely challenge our simple, Earth-based picture of what a habitable planet actually needs to look like. There's a genuinely beautiful technique astronomers use to study the hidden interior of stars, one that doesn't involve cutting anything open at all, but instead involves listening. Our own sun constantly vibrates, ever so slightly, its surface rippling with countless overlapping sound waves generated deep within its churning interior. Sensitive instruments can detect these tiny surface movements, and by carefully studying their patterns, scientists have essentially learned to read the sun's internal structure the way a physician might read a heartbeat, an entire instrument panel quietly trembling with signals rising up from far below. Instead of cutting the sun open, which is obviously impossible, scientists simply listen to its vibrations instead, and those subtle patterns turn an otherwise ordinary glowing disk into something almost transparent, at least to sufficiently careful mathematics. Other stars pulse, tremble, and resonate in remarkably similar ways. Space telescopes can measure the extraordinarily tiny changes in brightness that occur as these internal waves move through a star's interior. Those brightness variations might look slight at first glance, but they carry remarkably rich information. By carefully studying the specific frequencies of these oscillations, a technique called astroseismology, astronomers can estimate a star's size, mass, age, internal rotation, and evolutionary stage, all without ever needing to physically visit it. This proves especially useful because stars are usually visible only as simple points of light from Earth. Astroseismology effectively gives them an inner structure we can actually study in detail. It can distinguish between stars that look nearly identical from the outside, but that are, in reality, at very different stages of their internal evolution. This technique has also considerably improved the study of exoplanets, since knowing a host star's properties more precisely helps researchers determine the true size and age of any planets orbiting it as well. The underlying idea is wonderfully elegant. Stars have music too, just written in light rather than in sound. When scientists learn to decode that hidden rhythm, they learn what's genuinely happening beneath surfaces that no spacecraft could ever hope to physically touch. Some stars pulse specifically because their outer layers trap and then release heat in a repeating, almost rhythmic cycle. In certain types of stars, changes in opacity within specific partial ionization zones can create a natural, self-sustaining engine for pulsation. When one of these layers traps heat, internal pressure builds, and the star's outer layers physically expand outward. As that expansion changes the conditions within the trapping layer, heat escapes more easily, and the star contracts back inward again. This entire cycle can repeat with striking, almost metronomic regularity. The result is what astronomers call a variable star, one whose brightness rises and falls steadily, almost like a slow, patient breath. These pulsating stars matter, not only because they're physically fascinating in their own right, but because their steady rhythms reveal properties that can be measured accurately across enormous cosmic distances. Their changing brightness over time becomes a genuine signature of their internal physics. Instead of picturing a star as a simple, fixed lamp hanging in the darkness, we begin to see it instead as a genuinely dynamic body, made of layers that store, release, and continuously respond to heat. Pulsation turns a star's otherwise hidden internal structure into something visible, measurable, and precisely timed. One particular family of pulsating stars, called Cepheid variables, ended up helping astronomers measure the true scale of the entire universe. Cepheids share a crucial, reliable relationship between their pulsation period and their true, intrinsic brightness. The longer a Cepheid's period, the more luminous it genuinely tends to be. Once astronomers properly understood this relationship, thanks in large part to Henrietta Leavitt's careful work, they could compare a Cepheid's true brightness against how faint it actually appears from Earth, and that difference alone reveals its distance with real precision. This made Cepheids into genuine cosmic measuring rods. They helped demonstrate that certain fuzzy, faint patches of light in the night sky weren't nearby nebulae drifting somewhere inside our own Milky Way, but entirely separate galaxies, sitting far, far beyond it. That single discovery dramatically expanded humanity's entire sense of scale for the universe almost overnight. Cepheids have also helped calibrate later, even more far-reaching distance measurement methods, including the very type I supernovae we discussed earlier tonight. Their importance ultimately comes down to sheer regularity. A star that predictably brightens and dims on a steady, repeating rhythm can tell you, with real confidence, exactly how far away it actually is. The true scale of the cosmos was never discovered by physically traveling through it. It was discovered by patiently watching stars breathe. Let's turn briefly to some of the most persistently brilliant objects the universe has ever produced, and to one of the newest tools humanity has built for studying the earliest moments of cosmic history. At the centers of certain distant galaxies, supermassive black holes are surrounded by disks of gas spiraling steadily inward. As that material falls, it heats to genuinely extreme temperatures and releases an enormous amount of energy before ever crossing the point of no return. The result can be a quasar, one of the single brightest, most persistently steady sources of light anywhere in the observable cosmos. A single quasar can shine more intensely than every star in its entire host galaxy combined. Some launch narrow jets that stretch across distances larger than their host galaxy itself, driven by powerful magnetic fields and streams of extraordinarily energetic particles. Because many quasars sit at genuinely enormous distances, their light often began traveling when the universe was considerably younger than it is now, making them brilliant beacons reaching us directly from deep in cosmic time. By studying them carefully, astronomers learn about early black hole growth, early galaxy formation, and the faint, diffuse gas drifting in the space between galaxies. A quasar, in a strange and genuinely poetic way, is powered entirely by darkness, and yet it becomes one of the most luminous signatures that matter is capable of leaving behind anywhere in the universe. One of humanity's newest tools for studying this deep cosmic history is a space telescope specifically designed to look into infrared wavelengths, which turns out to be essential for studying the very earliest galaxies. As the universe expands, light traveling to us from extremely distant objects gets stretched considerably along the way. What began as ordinary ultraviolet or visible light can arrive here, after billions of years of travel, as infrared radiation instead. This telescope's large, gold-coated mirrors collect that faint, ancient glow with extraordinary sensitivity, allowing astronomers to examine galaxies from an era when the universe was still genuinely young, still actively assembling its very first large-scale structures. Some of these early galaxies appear surprisingly bright or surprisingly mature for how early they formed, which has sparked entirely new questions about exactly how quickly stars and galaxies were able to assemble themselves in the young universe. This same telescope can also see directly through thick cosmic dust that ordinarily blocks visible light, revealing hidden regions of active star birth that would otherwise remain completely invisible. It isn't simply capturing beautiful pictures for their own sake. It's actively measuring chemistry, motion, and history in objects sitting near the very edge of observable time itself. With a telescope this sensitive, cosmic dawn is no longer simply an abstract idea confined to theory. It has become an actual place we can genuinely investigate, one faint, ancient photon at a time. Some galaxies harbor black holes carrying billions of times the mass of our Sun, and their sheer existence challenges some fairly simple assumptions about how quickly anything that large could possibly grow. To reach such an enormous mass, these giants must have either gathered enormous quantities of infalling material over cosmic time, or merged repeatedly with other black holes as their host galaxies collided and combined. What makes this especially puzzling is that some of these supermassive black holes existed when the universe was still remarkably young, leaving astronomers with a genuinely difficult question. How did they manage to grow so quickly? Did they begin their existence as unusually massive seeds to start with? Did surrounding gas fall into them at an unusually extreme, sustained rate? Or did conditions in the early universe simply create unusually perfect feeding conditions that no longer exist today? Astronomers search for answers by studying distant quasars, nearby galactic centers, and increasingly detailed computer simulations of cosmic evolution. These immense black holes are never minor details within their host galaxies. Their energy output can heat surrounding gas, launch powerful jets, and directly influence whether or not new stars are able to form nearby at all. The scale involved is almost absurd to sit with. A region smaller than our own solar system can end up helping regulate the fate of billions of stars scattered across an entire galaxy. Spiral galaxies owe much of their striking visual structure to a subtle, elegant piece of physics hiding within their gently rotating disks. The arms of a spiral galaxy aren't fixed rows of the exact same stars, turning together like rigid spokes on a wheel. They're better understood as patterns of density, slowly moving through the galactic disk over time, a little like a traffic jam that persists on a highway even as individual cars continuously enter and leave it. Gas entering one of these dense regions gets compressed, which encourages fresh star formation to occur there, and the resulting young, hot stars light up the arm with a distinctive bluish brilliance, at least until they eventually die, or gradually drift away from the pattern that originally triggered their birth. This is precisely why spiral arms stand out so dramatically in photographs of distant galaxies. They're marked by short-lived, brilliant stars, glowing gas, and dark, winding dust lanes, all tracing out regions where future stars may still be quietly forming. Older, longer-lived stars are spread far more evenly throughout the disk and central bulge, contributing to a galaxy's softer, more uniform background glow instead. Spiral arms, in other words, aren't merely decorative. They're a direct sign of ongoing activity, revealing exactly where a galaxy is still actively rearranging its available gas into brand new generations of stars. A spiral galaxy was never a static pinwheel, frozen in place. It's a genuinely rotating system, where a persistent wave pattern quietly guides where and when new stars are born, across truly enormous distances. Beyond the bright, visible disk, beyond the spiral arms and the dense central bulge, our own galaxy sits embedded within a much larger, largely invisible halo. Part of that halo contains old stars and the globular clusters we discussed earlier, but the overwhelming majority of its total mass appears to be dark matter instead. Astronomers infer this indirectly from the motion of individual stars, gas clouds, satellite galaxies, and long stellar streams scattered throughout the halo. The visible Milky Way, the bright spiral most people picture when they imagine our galaxy, is really only the luminous inner portion of a considerably larger gravitational structure. This surrounding halo may stretch far beyond the outer boundary of where most visible stars actually shine. Its mass helps hold satellite galaxies safely in orbit and directly influences how captured stellar streams move as they slowly wrap around the galaxy over billions of years. Mapping this halo directly is genuinely difficult, since it can't be observed visually at all. Astronomers instead rely on the motion of distant tracer stars and dwarf galaxies to estimate its overall shape and total mass. The resulting picture quietly changes how we might imagine our own cosmic home. The Milky Way isn't simply a glowing, familiar spiral hanging in the darkness. It's a comparatively small, bright island, embedded deep within a vast, mostly invisible envelope of matter, stretching out far beyond anything a naked eye could ever hope to see. Let's pause once more, just for a moment. There's genuinely no need to hold on to every idea we've walked through tonight. The halos, the arms, the ancient stars quietly hiding in the galaxy's outer reaches. Let it all soften now. The way distant starlight softens the longer you let your eyes rest on it without trying to focus too sharply. We're nearing the end of tonight's journey, just a little further to go, back toward the underlying method that makes all of this possible in the first place, and then gently, quietly, back toward rest. What ties every single idea we've explored tonight together isn't simply that they sound extraordinary, though they genuinely do. It's that every one of them can be tested again and again against the actual universe. Ideas about invisible matter, about expanding space, about stellar death, about black holes that bend time itself. All of them sound almost like fantasy at first. Yet they've survived and continued to survive, precisely because real observations keep pointing toward them again and again from entirely independent directions. Telescopes collect light arriving from unimaginably distant objects. Detectors register individual particles and, more recently, entire gravitational waves. Spectra reveal detailed chemistry from across the universe, based on nothing more than the specific colors of light a distant object happens to emit. Mathematical models make specific, falsifiable predictions, ones that genuinely can fail if reality doesn't cooperate. And that, ultimately, is what gives this entire field its quiet power. Astrophysics asks enormous, almost unreasonable questions. How do stars actually shine? Why do galaxies hold together at all? What happened in the exact instant the very first atoms formed? But it insists on answering those enormous questions with careful, patient measurement, rather than simply with imagination alone. The result is a universe that turns out to be more surprising than any myth ever invented, and yet never quite beyond genuine human understanding. It's a place where wonder never has to compete with evidence. If anything, the wonder only grows stronger, precisely because the evidence backing it up is entirely real. For most of human history, the stars above inspired myth, guided navigation, shaped calendars, and stirred quiet wonder in anyone willing to look up. Modern science never took any of that wonder away. It simply gave it sharper, more precise tools to work with. A single point of light can now be measured for brightness, color, chemical fingerprint, motion, age, and distance, all at once. A patch of apparent darkness can reveal hidden dust, cold drifting gas, or the quiet gravitational pull of matter we'll never directly see. A single faint signal, captured by a sensitive detector, can announce a violent collision that actually happened long before complex life had even appeared on Earth. What makes astrophysics so genuinely compelling isn't simply the grandeur of its claims. It's that every single one of those claims gets checked, patiently, against the real sky. The universe becomes a story with actual evidence embedded in every chapter. Some of its pages are written in light. Some are written in particles, in gravitational waves, or in patterns of motion too subtle to notice without careful instruments. Many pages remain entirely unread, even now, and yet the underlying method stays steady, chapter after chapter. Ask a bold question, build a sufficiently careful instrument, compare the answer honestly against reality, and let the cosmos itself correct you wherever you happen to be wrong. Under a sky studied this way, the night above you stops being simply a ceiling. It becomes, quietly, an invitation. It's worth sitting, just for a moment, with the sheer scale of everything we've been discussing tonight. The observable universe, the portion of the cosmos whose light has actually had time to reach us since the beginning, spans somewhere around 90 billion light-years across, containing, by current estimates, somewhere in the range of 100 billion to 2 trillion galaxies, each one, in turn, containing anywhere from a few million to several trillion stars of its own. Sit with that for a moment, and the number becomes almost impossible to hold on to meaningfully. And even that staggering total represents only the observable portion, the part whose light has had enough time to reach us since the universe began. The universe beyond that boundary may be larger still, perhaps enormously larger, simply hidden from view because its light hasn't had time to arrive yet. And given the accelerating expansion we discussed earlier, some of it may never arrive at all. It's genuinely difficult to hold a number like that in your mind for very long without it slipping away into abstraction. Perhaps that's all right. Perhaps some numbers are only meant to be visited briefly, acknowledged, and then gently set back down, the way you might glance at a night sky too vast to fully take in, and simply let yourself feel small within it, rather than trying to measure it all at once. We touched earlier on the narrow, powerful jets that some active black holes launch outward from their surrounding accretion disks, and it's worth lingering on them a little longer, since they represent some of the largest coherent structures the universe has ever built. These jets are threaded and powered by intense magnetic fields, anchored deep in the spinning, twisted spacetime immediately surrounding a black hole, and they can stretch for hundreds of thousands, sometimes millions, of light years beyond their home galaxy, dwarfing the very galaxy that produced them in the first place. When one of these jets happens to point almost directly toward Earth, an effect called relativistic beaming dramatically amplifies how bright and energetic the entire system appears from our particular vantage point, a category of object astronomers call a blazar. Viewed from nearly any other angle, that same underlying object might appear comparatively faint and unremarkable. It's a genuinely humbling thought. Some of the most persistently powerful individual objects in the sky may owe much of their apparent brilliance not to being fundamentally different from their quieter cousins, but simply to how fortunate, or unfortunate, their particular jet happens to be aimed relative to our own tiny, distant vantage point. All of this naturally raises a quieter, more personal question, one that sits underneath almost everything we've explored tonight. Given how many stars and planets fill even a single galaxy, could any of them host life somewhere else entirely? Astronomers approach this question the same careful, patient way they approach everything else, by defining what's called a habitable zone, the range of distances from a star where a rocky planet could plausibly maintain liquid water on its surface, neither boiled away by excessive heat, nor permanently frozen by insufficient warmth. Thousands of exoplanets have now been confirmed, and a meaningful number of them orbit comfortably within their star's habitable zone. Being in that zone doesn't guarantee habitability by any means, since a planet's atmosphere, its magnetic field, its geological activity, and countless other factors all matter enormously as well. But it does narrow the search in a genuinely useful way. Researchers now study the atmospheres of some of these distant worlds directly, looking for chemical signatures, combinations of gases that might hint at biological activity, without any real certainty of what they might eventually find. No confirmed evidence of life beyond Earth exists yet, but the search itself has become genuinely rigorous, patient, and increasingly well-equipped, less a matter of hopeful speculation now, and more a matter of steadily improving instruments, asking an old, quiet question with newly sharpened tools. On the very largest observable scales, Even entire clusters of galaxies aren't simply drifting randomly through space. Careful measurements of galaxy motion across large regions of the sky have revealed that our own galaxy, along with many of its neighbors, appears to be slowly flowing toward a specific, massive concentration of matter, informally nicknamed the Great Attractor, hidden partly behind the obscuring dust and gas of our own galactic plane. The exact nature of this enormous structure remains difficult to study directly, precisely because so much of it sits behind the Milky Way's own crowded disk, blocking a clear view in visible light. What astronomers can measure is the resulting motion. Galaxies across an enormous volume of space are consistently drifting in a shared direction, pulled along together by the combined gravity of everything gathered there. It's a genuinely strange thing to consider. Even galaxies, among the largest individual objects the universe builds, are still caught up in even larger patterns of motion, gently, patiently flowing along cosmic currents shaped by gravity acting across almost unimaginable distances. There's a genuinely strange puzzle buried inside the physics of black holes that we only touched on briefly earlier, one that continues to challenge physicists even now. When ordinary matter falls into a black hole, it seems to disappear from the observable universe almost entirely, leaving behind only its mass, its spin, and its electric charge, as we discussed. But ordinary quantum physics insists that information, the detailed, specific arrangement of particles that made up whatever fell in, should never be truly destroyed, not even under the most extreme circumstances imaginable. So where does it go? If a black hole eventually evaporates completely through the slow process of Hawking radiation we discussed earlier, what happens to all of that seemingly lost information? This tension between what general relativity predicts and what quantum mechanics demands is often called the black hole information paradox, and it remains one of the most actively debated open problems in modern theoretical physics. Some researchers suspect the missing information is somehow encoded subtly within the outgoing Hawking radiation itself, in ways too complex for current mathematics to fully untangle. Others suspect our understanding of space-time itself may need to be revised at the most fundamental level to resolve it. No confirmed answer exists yet, but the puzzle itself is a genuinely humbling reminder that even after a century of extraordinary progress, black holes are still holding onto a few of their deepest secrets. We touched earlier on how two colliding neutron stars can forge heavy elements and send gravitational waves rippling outward, but that same basic story, two collapsed stars gradually spiraling together, was actually first confirmed decades earlier through nothing more than remarkably patient, old-fashioned observation. In the 1970s, two astronomers, Russell Hulse and Joseph Taylor, discovered a pulsar locked into a tight binary orbit with a second, unseen neutron star. Because the pulsar's radio signals were so precisely timed, the pair's orbit could be tracked with extraordinary accuracy, year after year, for decades. General relativity made a very specific, testable prediction about a system exactly like this one. As the two neutron stars orbited each other, they should gradually lose orbital energy by radiating gravitational waves outward, causing them to spiral slowly closer together and complete each orbit ever so slightly faster over time. That's exactly what decades of careful, patient observation eventually revealed. The measured decay of the orbit matched Einstein's prediction with remarkable precision, long before any instrument on Earth had ever directly detected a gravitational wave passing through it. This discovery earned Hulse and Taylor the Nobel Prize, and it remains one of the most quietly beautiful stories in the history of astrophysics. Two dead stars, locked in an ancient, patient orbital dance confirmed one of general relativity's strangest predictions decades before humanity built anything capable of feeling that same cosmic ripple directly. Given everything we now understand about dark energy's steady acceleration of cosmic expansion, it's worth asking, gently, what kind of future the universe might actually be heading toward. If dark energy continues behaving the way current measurements suggest, the universe's expansion will likely keep accelerating indefinitely, gradually carrying galaxies farther and farther apart from one another. Over unimaginably long timescales, stretching trillions of years into the future, stars across the universe will slowly exhaust their available fuel, one by one, and stop forming altogether, as the raw gas needed to build new ones becomes increasingly rare and thinly spread. Existing stars will fade into white dwarfs, neutron stars, and black holes, and even those remnants, given enough time, may eventually evaporate through the same slow process Hawking radiation predicts. This distant, patient future is sometimes called the heat death of the universe, or the Big Freeze, a state of maximum entropy where energy is spread so evenly across so vast a volume that essentially nothing interesting can happen anymore, forever. It's a genuinely strange thing to consider on a quiet night like this one, that the universe itself may be moving, slowly and patiently, toward its own kind of rest. There's no need to feel unsettled by this. It lies so unimaginably far in the future, trillions upon trillions of years away, that it holds no real bearing on anything happening tonight, in this room, in this moment. If anything, it's oddly reassuring. Even the universe, on its own vast timescale, seems to be moving steadily towards something like sleep. It's worth pausing, too, on exactly how astronomers manage to find planets around other stars at all, given that the planets themselves are almost always far too faint and far too close to their stars' overwhelming glare to photograph directly. Most confirmed exoplanets have been discovered indirectly, through two complementary techniques. The first, called the transit method, watches a star's brightness closely over time, waiting for the extremely slight, regular dimming that occurs whenever a planet happens to pass directly in front of it, from Earth's particular point of view, blocking a tiny, measurable fraction of its light. The size of that dip reveals the planet's approximate size, and the regular timing between dips reveals its orbital period. The second, called the radial velocity method, looks instead for a star's own subtle wobble, caused by the gravitational tug of an orbiting planet pulling it very slightly back and forth. That wobble shows up as a tiny, rhythmic shift in the star's light, alternating gently toward blue and then red as it moves fractionally toward and away from Earth. Neither method requires ever actually seeing the planet itself directly. Both rely entirely on the planet's subtle influence over its parent star's light. Between these two techniques, and a handful of rarer methods like gravitational microlensing, astronomers have now confirmed thousands of worlds orbiting other stars, transforming what was once pure speculation into a genuinely well-populated, carefully measured catalog of entire distant solar systems. And so, gently, we come back from the farthest edges of the cosmos. Tonight we've drifted through the strange, beautiful machinery of astrophysics together. We've watched time itself bend and stretch near the edge of a black hole, and seen how ancient, long-dead stars quietly shaped the very atoms that make up your body. We've followed galaxies as they gather, collide, and slowly grow across billions of years. We've listened for ripples moving silently through space-time, traced invisible matter purely through its gravity, and looked all the way back toward the very first light that ever managed to travel freely through the universe. We've wandered among neutron stars, glowing nebulae, distant exoplanets, and the hidden, patient forces that quietly stretch space itself a little further every single day. And through all of it, one single idea kept returning again and again in different forms. The universe is not still. It is moving, changing, forming, fading, and beginning again in ways too vast to hold all at once inside a single mind in a single evening. But you don't need to hold all of it right now. Let the stars soften back down into simple, quiet points of light. Let the galaxies drift a little farther away, exactly the way they always do, whether anyone happens to be watching or not. Let the great, enormous questions rest for a while, like instruments finally falling silent after a long, beautiful, unhurried song. There's nothing left to figure out tonight. No number to hold on to, no name to remember, no equation to carry with you into the morning. Let your shoulders loosen completely into whatever is holding you up right now. Let your breathing find its own slow, natural rhythm, without needing any help from you at all. Imagine the night sky stretching directly above you, wide and steady, every distant star quietly holding its place, exactly where it belongs. The universe will keep turning regardless. The ancient light will keep traveling patiently towards someone, somewhere, whether or not you're awake to receive it. And for now, you can simply rest. Here's the mirror I want to leave you with tonight. Everything we explored together, the bending of time, the forging of gold inside a dying star, the invisible scaffolding holding entire galaxies in place, all of it eventually leads back to the same quiet point. You are not separate from any of this. The calcium in your bones was built inside a star. The iron in your blood crossed the galaxy long before it ever became you. Even the simple, ordinary act of resting here right now, breathing slowly in the dark, is happening on a small, rocky world, drifting through a spiral galaxy, itself drifting through an expanding universe, all of it moving together, unhurried, exactly the way it always has. You don't have to understand all of it to belong to all of it. You already do. If you enjoyed this journey tonight, you're always welcome to like this video, subscribe to Somniora Mind, or leave a thought in the comments below. It helps other curious, sleepy minds find their way here too, one quiet mind at a time. Rest now. You've earned it. Good night.